All right, everyone, we should be seeing us right now. If there's any problems, let us know. Uh, I will be keeping a close eye on everything. My name is Braden Walker, and I'm with Math and Stats Society at USask, and I'm pleased to introduce our second last math talk of the semester with Maddie Berezowski, a first-year PhD in applied mathematics under Dr. Sowa. She's coming over from her a Master of Science in Physics under Rainer Dick, and your main topics of interest are quantum operators. So I think we're going to learn about one right now. So I'm going to let Maddie take it away.
Great, thank you so much.
There we go.
Okay, there's my screen. Okay. So, thank you guys so much for having me. I really appreciate this opportunity. I'm going to be talking about Toeplitz matrices and operators today. So first, we'll go over some definitions, and then we'll talk about Toeplitz and Lorentz operators and their relation to Fourier series, as well as their identification as multiplication operators. We will also talk about their spectra. And finally, we'll talk about how Toeplitz operators are related to my research. So first, a Toeplitz matrix is a matrix whose entries are constant along each diagonal. And these diagonals are the ones that are descending from left to right. So a Toeplitz matrix does not have to be square, but we will only be considering square Toeplitz matrices here. So we can write a square n by n Toeplitz matrix like this. So let's note that the elements can be complex valued. And so we see in the diagonal, we've got A0, it's constant. And then in the subdiagonal, we have A1. Below that, A2. And then all the way down, we've got AN minus 1 in the bottom left. And similarly, in the superdiagonal, we've got A minus 1, above that A minus 2, and then we go all the way up to A 1 minus n in the top right. So the matrix entry corresponding to the row I and column j has this lowercase a with index I minus j as its entry. So here is an example of a Toeplitz matrix. We've got 2 along the diagonal, 1 in the superdiagonal, and 3 above that, and then 4i. And then in the subdiagonal, we've got I, and then minus 1 and 0 in the bottom left entry. So pretty straightforward. So if we have an n by n Toeplitz matrix with this indexing convention with the row minus column thing, and the entries wrap around periodically so that aj is equal to an minus j for j between 1 and n minus 1 inclusive, then we can call it a circulant matrix. So an n by n circulant matrix has this form. So we have A0 in the diagonal again. However, in the subdiagonal, we've still got A1, but in the top right, we also have the matrix entry A1. Then in the diagonal below the subdiagonal, we have A2. And then right here in the top right, we have a row of A2s. So we can see that it wraps around periodically. And we can also notice that in the rows and columns, we have cyclic permutations of our elements. So if we look at this first column on the left, we've got entries A0 up to AN minus 1. And then in the column beside it, we have the same thing, except the bottom entry is now on the top. So an minus 1 is on the top now. And similarly for the next column, we've got the element that was in the bottom entry as the top entry for the next one, and so on and so forth. So these are cyclic permutations, and we see the same thing happens in the rows as well. So we see the last entry, A1 for the top, becomes the first entry for the next row, and so on and so forth. So this is a circulant matrix. And so here's an example. So we can even start at the top right. So we've got 5, 4, 3, 2, 1, and then 5, 4, 3, 2. And so we'll notice that the diagonal only appears once, those entries. And so now we are going to consider operators. So if we have a matrix that's infinite, then we can call it an operator. And an operator that can be represented by a semi-infinite Toeplitz matrix is called a Toeplitz operator. So we can represent a Toeplitz operator by this semi-infinite matrix here. And what we mean by semi-infinite is that the entries go on forever to the right, and they go on forever as the entries go down as well. If we have a doubly infinite Toeplitz matrix, then we call it a Laurent operator. So we can write the Laurent operator like this, and we see that the elements extend into infinity. There are entries in every direction infinitely. And so that's why it's doubly infinite, right? It doesn't have any corners. This semi-infinite Toeplitz operator has a corner on the top left. But a Laurent operator doesn't have anything like that. And we can see in this Laurent operator, we have cyclic permutations of our elements again, in the same way that circulant matrices do. And we see that Laurent operators are actually the infinite dimensional analog of circulant matrices. Okay, so we've got our definitions now that we need. And we can move on to how Toeplitz and Laurent operators are related to Fourier series. So first, okay, we need one more definition, which is the symbol of a Toeplitz matrix or operator, or Toeplitz operator, or Laurent operator. And it is defined by this function f of z. So we're summing over n, and we've got an z to the n. And z is a complex number, and remember, these an are just our matrix entries, where n is equal to the row minus the column. And so, of course, n is going to be different depending on what kind of operator or matrix we have. For a Toeplitz matrix, we go from 1 minus n all the way up to n minus 1. A Toeplitz operator, we go from n equals 0 to infinity. And we'll talk about that a little bit more later, but we're mostly concerned with Toeplitz operators that look like this for this discussion. So from n equals 0 to infinity. And a Laurent operator is going to go from n equals negative infinity to positive infinity. So now let's restrict the complex number z to be in the unit circle, which we'll denote by this boldface T. So it's the set of all complex z with complex norm equal to 1. And we can write z equals e to the 2 pi I x for x between 0 and 1. So x parameterizes the circle. And if you'll remember, a general complex number we can write as r e to the I theta. But here we're on the unit circle, so r is just equal to 1. So plugging this in, the symbol now as a function of x can be written as the sum over n of an times e to the 2 pi I n x. And this is pretty special because this looks like a Fourier series. So we want to make sure that this is a Fourier series. So how can we do that? Well, we're going to consider only Laurent and Toeplitz operators for the time being, first of all. And we want to know when this sum here converges to a square integrable function over the circle. And so if this is satisfied, then we have a Fourier series. So this L2 of t, that is the space of square integrable functions, and f is a square integrable function if you take its norm or its absolute value and square it, then integrate over the circle or whatever space you're dealing with, and then take the square root. And if that number is finite, then the function is an element of L2 of this, in this case, t, the circle. So this sum is going to converge to a square integrable function when these coefficients, the sequence of coefficients, is in the space of square summable sequences. So this little L2 of z, that just means that if you take all of the sequence elements, take their absolute value and square them, then sum them together. If you have a finite number, then you are going to have a square summable function. And this z, that's the complex numbers, right? Because we're going from n equals negative infinity to positive infinity. And so if this condition is satisfied, then f is square integrable over the circle. And so in this case, this sequence an is the sequence of Fourier coefficients of f. And that means that we can write these an as the integral from 0 to 1 of f of x e to the minus 2 pi I n x dx. And another way to write these Fourier coefficients is f hat of n. And then we have this f of x, that's our symbol that we were discussing just a moment ago. For Toeplitz operator in particular, so because it is semi-infinite and not doubly infinite, it turns out that we actually have to restrict our attention to functions which are in the Hardy space, or sorry, the Hecke space, which is also called the Hardy space on the circle. And so f is in the Hecke space if it is square integrable on the circle, and all of its coefficients are 0 if n is less than 0. And so then we have that the coefficients, the sequence of coefficients is square summable. And so this is in L2 of n, and that's just making reference to the fact that we're going from 0 to infinity instead of indexing over the integers. Okay. So now we can talk about a certain property of Toeplitz and Laurent operators using this Fourier stuff. So we're going to consider a Laurent operator A with a symbol which is square integrable over the circle. And so we want to know, how does this Laurent operator affect a sequence that is square summable? So we'll take a function that is square integrable over the circle, so g, and it has a sequence of Fourier coefficients, and this sequence belongs to the space of square summable functions, or square summable sequences. And so we're going to denote this whole sequence as g hat. So it's going to be the sequence given by g hat of n, the Fourier coefficients of this g. And we're also going to call this Fourier transformation that takes g to g hat as curly f. Okay. So we want to look at how does this Laurent operator affect this square summable sequence. So we're going to look at the mth entry, right? So a good way to think about this is to compare it to a matrix acting on a vector. So we have, analogously, an infinite matrix or an operator acting on an infinite vector, which is a sequence. And so we are just doing matrix multiplication with infinite dimensions. Right, and the nth entry of g hat is g hat of n. And so remember, we have this way to write the matrix or the operator elements in terms of the row and column of mn as our row and column. Then we have the entry is equal to little a m minus n. And we've still got our g hat of n here. And we're summing from negative infinity to infinity here still. I just suppressed writing that. And so remember these ANs, these little ANs, they are the Fourier coefficients of our symbol, right? So it's f hat of m minus n, g hat of n. Okay, so we've actually found something that maybe you'll recognize here. So this is a discrete convolution. And so briefly what a convolution is it kind of tells you how one function, or I guess in this case, how one sequence kind of affects the other one. And so we write our convolution like this. So f hat and then star g hat of m. So this is our discrete convolution. And so we have a little theorem for our Fourier coefficients. We can actually write this convolution like this. So what do we have here now? So we took our Laurent operator and we acted it on some sequence g hat, and we're looking at the mth element. And it turns out that the mth element is the mth element of the Fourier coefficients of f times g. That's pretty neat. Okay, so what does this all mean? Why is this significant? So let's take our inverse Fourier transform. So we've got this here. And that's just by definition. And so we can use what we just figured out above here. So we can write our sequence fg hat as A acting on G hat. And so then, okay, well, what is G hat? It's this Fourier transform of G. So look, we've got some operator here, right? And its action on G, this function G, is equal to multiplication by F. So we can say that the action of A, our Laurent operator on G hat, is equivalent to multiplication of G by F. And so that means we can identify Laurent operators as multiplication operators. Toeplitz operators are, of course, a little bit different because they are semi-infinite and not doubly infinite. And so we identify them as multiplication and projection operators, right? So this projection that's involved is the projection from the space of square summable functions on the circle to the Hecke space. Okay. Moving onwards, we're now ready to talk about the spectra of Laurent and Toeplitz matrices and operators. So if you're a little bit familiar with this, you might see how this is going to lead to a discussion about spectra or eigenvalues. So first, we'll go over some basic definitions in case anyone isn't familiar with eigenvalues and vectors or forgot. So if we have a square n by n matrix, then a vector v, which is not equal to 0, is an eigenvector of M if it has a corresponding eigenvalue lambda, such that someone says you could say this is hecka cool. That's funny. Okay, so V is an eigenvalue of M, or an eigenvector of M, excuse me, if we have this eigenvalue here such that M acting on V is equal to lambda times V. So eigenvalues are nice because they're like the heart and soul of a matrix. So if lambda is an eigenvalue of our matrix M, then that means that the matrix lambda I minus M is not invertible. So this is equivalent. And so now we'll define the spectrum of our matrix M, denoted sigma of M, and it is the set of all eigenvalues of M. So we can write it as sigma of M is the set of all complex valued lambda such that the matrix lambda I minus M is not invertible, or lambda I minus M inverse does not exist. So hopefully you guys are familiar with that. If not, then just think of eigenvalues as something very, very characteristic to that matrix. So we want to generalize this notion of eigenvalues and spectra now to operators. So infinite dimensional matrices. And it turns out that this isn't very easy, and we actually need to put some restrictions on our operators before we're able to actually talk meaningfully about their spectra. So first we need M, which is an operator now. It has to be a closed operator. So a closed operator means that if we have some sequence of vectors that converge, a sequence UN that converges to U, and the action of M on these vectors un converges to V, then we have that M acting on U is equal to V. So that's a closed operator. And the other thing we need is for M to be defined in a Banach space. So that is a complete normed vector space. And we've been dealing with those. So no need to worry about that. Okay, so if we have a closed operator defined in a Banach space, then we can now define the spectrum of our operator M, which is the set sigma of M, which is the set of all lambda, complex valued lambda, such that the matrix lambda I minus M inverse does not exist or is not bounded. And so what does that mean to say a matrix is bounded or not? Well, if it's bounded, then its action, if you take, so the matrix is going to transform, or the operator is going to transform some vector or sequence. And if the new vector or sequence has a finite norm, then our matrix or our operator is bounded. If that's happens for all of our elements that it's operating on. So it is a generalization of the notion of eigenvalues. However, we'll note that eigenvalues and eigenvectors are defined in the same way as for matrices. So mv equals lambda v, then lambda is an eigenvalue and v is an eigenvector. However, there's one little tricky thing here. So the set of eigenvalues of an operator is actually a subset of its spectrum, generally speaking. So that means that there are elements of the spectrum that might not actually be eigenvalues, but they're still part of the spectrum. Okay, so now that we can talk about the spectrum of an operator, we're ready to go back to our Laurent operator A. And again, it has symbol f, which is square integrable over the circle. And we also have that g that we were talking about before, which is also square integrable over the circle. And we had gotten that we have this multiplication operator defined in terms of A. Acting on g is just f times g. So there we go. We have actually that we found eigenvalues, right? And so this multiplication operator is going to have the same spectrum as A, our Laurent operator. Okay, so that means that the set of eigenvalues of our Laurent operator A is actually the image of the circle under the symbol of A. So this is actually the full spectrum for a Laurent operator. The spectrum is equal to the set of eigenvalues in this case. And we want this to be a closed curve. So from now on, in order to ensure that we have a closed curve, we are going to demand that our symbol f is continuous. And it's still square integrable, but we also need it to be continuous now. So if A is a Laurent or Toeplitz operator with continuous symbol, f, which is also square integrable over the circle, then its symbol curve is the closed curve f of t. So it is the image of the circle under the symbol. And that is our symbol curve. So we can look at some examples now. So here we have f of z is equal to 0.4z minus z to the 5. So this is a finite sum. And of course, this is square summable. And we can also note that since it has a finite number of terms, it is also the symbol for some Toeplitz matrices, as long as the dimensions are large enough. So a Toeplitz matrix can also have a symbol that looks like this. It just depends whether or not it goes off into infinity and in how many directions. The size of the matrix, I mean. So I think this curve is very cute. I like it a lot. I found it all by myself. Wasn't that difficult, but so here is another example that I got from a book. It is called the Whale Matrix Symbol Curve. So it's this symbol here with all these terms. If we also consider, along with this symbol curve, this point here and this point here, and this curve, we have a little happy whale as well. So this is the whale matrix symbol curve, and here's a third example. So we've got this swoopy doopy thing going on here. And this is actually a really nice symbol curve. And we will come back to this because it's a good example. Okay. So if we consider now a circulant matrix instead of a Laurent operator, so remember this curve is the spectrum of the Laurent operator. It's all of its eigenvalues are wherever it's green. If we have a circulant matrix instead, rather than the spectrum being the image of the circle, it's going to be the image of the nth roots of unity. So that n comes from the fact that it's an n by n circulant matrix. And so this is very similar to how we got the spectrum of the Laurent operator, but we're just using a finite number of dimensions now. So we're going to call these roots of unity as boldface T with a subscript uppercase n. And it is the set of all complex z such that z to the power n is equal to 1. And so remember, in the complex plane, unity, the number 1, has infinitely many roots all along the circle, along the unit circle. So this spectrum of our circulant matrix is the image of the roots of unity under F. So F is going to transform these roots of unity instead of the whole circle, as long as our symbol is continuous and square integrable. So if we were to plot the spectrum of a circulant matrix, and I didn't have time to do this, otherwise I would have done it, but it would just be a bunch of dots that follow this curve. I'm not going to draw a whole bunch of dots, but that's what it would look like, is just dots instead of a whole curve. Now, the spectrum of a Toeplitz operator is more complicated. And so first we need another definition before we can talk about Toeplitz operator spectra. So the winding number of a curve about a point is the number of times the curve wraps around that point in the counterclockwise direction. So if a curve wraps around a point once, then we have a winding counterclockwise once, then we have a winding number of 1. So, if we have a point and, okay, so if it goes around this way once, winding number is 1, goes around again, winding number is 2. And if we come around back and go the other direction, then the winding number goes down by 1. So clockwise, wrapping around gives you a negative winding number. So this is just a very informal definition. And we'll denote the winding number of a symbol curve, f, about the point lambda, and lambda is not on the curve, by I of f lambda. So this is our winding number, I. And we'll note that if lambda is actually on the curve, then the winding number is undefined. So let's look at an example of the winding number. So here's our curve that I was talking about earlier. So we have a few different regions. So if we look at this region here, if we trace along the curve, we see that it wraps around any of these points in this area once. And this little area with the 2 in it, if we trace around the curve, we'll see that it wraps around those points twice. And we've got a negative 1 here because it goes in the clockwise direction. So it wraps around these points in a clockwise direction, so a winding number of -1 for all the points over here. I hope you guys can see my mouse. And then this 0 is pretty cool, this little triangle almost in the middle. Because what happens is we wrap around once, we actually wrap around it twice. But one of the times that it's wrapped around is in the clockwise direction, so that's -1. But then we also wrap around it in the counterclockwise direction once. So the total winding number is 1 plus -1 equals 0. Okay. So that's the winding number. And the spectrum of a Toeplitz operator now is the image of the circle under F. So it is the symbol curve, along with all of the points in the complex plane, except for the symbol curve, where the winding number is not equal to 0. So a non-zero winding number means that it's also in the spectrum. So here's our friendly little example again. And so the shaded area, all that green stuff, is the spectrum of the Toeplitz operator. Right, so the curve itself would be the spectrum of the Laurent operator with the same symbol. And the spectrum of the Toeplitz operator with this symbol is the curve along with everything that has a non-zero winding number. So that's pretty neat. And so I will summarize this now with a theorem. So we're going to let A be a circulant matrix or a Laurent or Toeplitz operator with a continuous symbol f, which is square integrable over the circle. So if A is a circulant matrix, then the spectrum of A is the image of the roots of unity under F. And so maybe we'll keep this with an uppercase N. And this is for an n by n circulant matrix. For a Laurent operator, the spectrum is going to be the symbol curve itself. And if we have a Toeplitz operator, then the spectrum is the symbol curve together with all the points enclosed by this curve that have non-zero winding number. So you can have a variety of different objects with the same symbol, but they would have different spectra depending on the type of operator that it is. And as for a general Toeplitz matrix that's not a circulant matrix, well, it's not so easy. But these ones are nice and easy to talk about, these guys, the circulant matrix, the Laurent operator, and the Toeplitz operator. Okay. So now we're going to talk about Toeplitz operators and V operators. So this is related to my research and why I need to know about Toeplitz operators. So a V operator is a sparse operator, and so sparse means that most of the entries are zero. There's some of them that are non-zero, but most of the entries are zero. And the locations of its non-zero or non-trivial entries are determined by a rational number, P over Q. So if P over Q is 3/2, for example, then we have a V operator, Q over P, V2 over 3. And this little picture here shows us the locations of its non-trivial entries. And again, non-trivial means non-zero. And so you can see that we have what looks like two lines with a slope of 2/3 and a slope of 3/2. Or, well, I guess negative if you're comparing it to lines, but that's a V operator in a nutshell. So there are infinitely many subspaces which are invariant under the action of the V operator VQ over P. And so an invariant subspace means that if you take an operator and act on this subspace, the result is still going to be in that subspace. And that's what it means for it to be an invariant subspace under that action. And so we can represent our operator, VQ over P, in an invariant subspace, as it turns out, by a tridiagonal matrix, which is 0 on the diagonal. So this is starting to sound like a Laurent operator, or sorry, a Toeplitz operator, right? And it's sounding like a Toeplitz operator, right? Because it doesn't extend into infinity in every direction. But let's dive into this a little bit more. So we represent VQ over P in our invariant subspace with a tridiagonal matrix. And the diagonal itself is actually 0. So in the case where the entries are constant along the subdiagonal and constant along the superdiagonal, we have a Toeplitz matrix, right? So these invariant subspaces are, generally speaking, finite dimensional. And so we would have a Toeplitz matrix that represents our operator in this invariant subspace. And so we have the way that the V operator is defined. If they're constant, then we have that these are all the complex conjugate in the subdiagonal of the superdiagonal. In particular, though, if Q is equal to 1, then we end up with an infinite dimensional invariant subspace. So then we're dealing with V1 over P, and it is represented by a Toeplitz operator in that invariant subspace. And so why do we care? So Toeplitz operators and Lorentz operators are actually a really important area of research because there aren't very many operators whose spectra we know how to calculate explicitly. So we would really like to be able to learn how to calculate the spectra of all sorts of operators, but that's not so easy. Laurent and Toeplitz operators, on the other hand, we know how to do that. We can get their spectra. V operators, which we've learned we can represent as Toeplitz operators or matrices in certain invariant subspaces, we can use them to examine more interesting operators. So we can write certain quantum operators as sums of V operators. And V operators are also closely tied to number theory. The P over Q stuff has a lot of really interesting things to do with number theory. And maybe I can talk to you guys about that some other time. So the whole idea of this then is we're trying to kind of fuse together number theory, operator theory, and quantum physics using V operators. Okay. So here are my references. I'm just learning about these operators myself too for my research, and so these 3 books are really great. So check them out if you want to learn more. And thank you so much for your attention. Please let me know if you have any questions.
I'll be coming back on camera for a second just to clap and thank you, Madeline. This is definitely something that's way out of my element, but I feel like as a stats major, I say that with every math talk that we do. Yeah, if there's any more questions from the chat, please get that in right now. If not, we can wrap this up. But yeah, thank you again. This is great.
Yeah, thank you guys so much.
Just give chat a minute or so to collect themselves.
Yeah, a chance to type something up.
Thanks and claps from Mahmood in chat.
Thank you very much.
Oh, the Dementor, Robert, has a question.
Okay. Yeah, no worries.
Robert, you can also come into the question queue and ask it yourself. Like you can come in and voice if you want.
You're welcome. And thank you, Sean, for the lovely thumbnail as well. Okay. About the Fourier transforms. As the eigenfunctions are more or less Hermite polynomials, are there any Hermite polynomials in the background happening here? Oh gosh, I really don't remember much about Hermite polynomials, to be honest. Actually, I think that's something that I'll have to look into. But I can't actually answer your question. I'm sorry. Okay. And someone says, are there any interesting things when examining the minors of these matrices? Okay, so you're going to have to forgive me. I come from a physics background and my math is a little bit rusty. So I'm not sure what a matrix minor is. The determinant of, where did it go? A smaller square matrix cut down from A. Oh, okay. Oh, right. Okay. I know those. Okay. Now, where did my house, my computer? Okay, here we go. Are there anything interesting? Possibly. I haven't actually looked into it myself. That's another thing I will have to check out.
All right. I think, see if there's anything more coming in, but I will thank you again.
Yeah, thank you guys.
For anyone who is watching this, who is interested, we have our Pi Day celebration in collaboration with the department coming up on Monday, the 15th, so the day after Pi Day. and as well as our general meeting. So if anyone here is interested in becoming involved next year, on April 1st, we'll be having our general meeting and elections for the next year. So thank you, Madeline. Thank you for watching. I will be closing the stream now. So have a great one.